Everyone, welcome to today's first talk by Professor Om Damani, who will be talking to us about JalTantra, which is a system designed by him and his team to improve the practice of rural water network design in India. This is an award-winning system, and we are very excited to learn more about it. So over to you, Om.
Thanks everyone for joining. So yes, I'm Om, but like she said, a work of this magnitude does not happen without the support of large number of people and participation. So this is the team JalTantra and some of the prominent members from the past. Now the top row contains the students, the main people really for any such project in a college who have designed the system or are working on different aspects of it. You see, they are PhD students, master's students, BTech students. All these students are mostly guided or co-guided by myself, Professor Pradeep Kalbar from CUs, and Asutosh Mahajan from IEOR. And of course, Professor Milind and Puru have been part of our journey from beginning as a part of the water group. And of course, in the bottom row, we have the key players from our project. See, Raj Desai, the external project coordinate, who was our interface, like we say, between the theory and the practical. And Pooja Prasad was our internal research coordinator in the beginning of the project. And of course, there were TDS engineers who have applied this to a lot of real life problems. So these were the main players, but actually there were many more students. Like there were 5 MTech theses from CSC, 7 MTD theses, MTD Master of Technology and Development from Sitara, with several students as part of the water group, and 40 or so TDSL. TDSL is Technology and Development Supervised Learning Project, which requires students to go out. So for, I think, more than 40 summer students have done the TDSL course. Summer or otherwise, summer interns, but the TDSL is offered throughout the year and the interns. And in particular, TDSC, the Technology Development Solution Cell, of whom I am one of the coordinator, along with Puru and Priya. So we have TDSC has reviewed hundreds of schemes. And of course, its mandate is bigger than a rural water scheme, but RWS forms a big part of it. And I would say the biggest award I feel we got was when one of our engineer got a threat call from a contractor. So I think that day we felt, yes, whatever we are doing is useful. It's not all a waste. Yeah. The work, of course, involved being grounded, understanding ground reality, as I will talk throughout the hour today. And I have personally visited over 100 rural drinking water schemes over these years with all these students and colleagues. So the background in which the work started, I joined in 2004 December, and Professor Soni and others in Sitara started around the time where he started work in the drinking water area. In 2005, the Gudwanwadi check dam. I mean, there were news from water distress from different parts of the state all through. Unfortunately, that news stream never stopped. But so one of the earlier first project was this Gudwanwadi check dam project. And then after that, there was this review of Jal Swaraj. Then there was a feasibility study done for the entire North Karjar, and then Anjab Sugwe scheme. So all this work was going on in by Professor Soni's lead. And I was a silent participant, meaning I was not an active participant. I went on some of the trips. I attended several of the presentations, and I was just trying to figure out, what should I be doing? What is the problem? And the use of, I mean, various tools, the various approaches were being formed up across these projects. So out of this came our approach for what we call the, IT research in water, the water group with Milind and Puru. And we said, look, first you have to start from grassroots level and understand the problem from the key stakeholder, the people who are affected, the villagers, the gram panchayats, the local NGOs, and then do a system level analysis of the relevant government programs and schemes. And then after that, you can bring the technical tools, modeling, simulation, optimization, other thing, and finally give the planning input. So of course, but the engagement has to start at the bottom. And of course, as you bring more and more tools, you move away from that. So you have to be aware of this. And this approach extends to all the IT work. I am advisor to several government departments on their IT infrastructure. And I have always tried to connect with the grassroots level people who are most affected. And that does make a difference in the approach we bring to solve a problem. So coming back, this my direct involvement started when the NGO Disha Kendra contacted us. So there was, like I said, this North Karjat, there was a particular summer was particularly bad. And they said, what can we do? We can gherav the collector, demand water, but how can IIT help us? And actually, that phrase stayed with me. And later on, I say now when I talk to NGOs, I said you should gherav the principal or the director of a local engineering college and say solve our problem. Just gheraving the collector is not going to be enough. So we offered several TDSL projects, and through them, what we realize is that the financial, social, and technical are all mixed, and each problem will have some component from all of them. So the in a scheme is designed, suppose it for whatever reason it has certain technical problem, either due to bad design or due to bad implementation or maintenance or something, and then the scheme starts failing. Usually it's not that it doesn't work for day one, at least most schemes they start working, but slowly they develop problem. Then some of the villagers pull out and refuse to pay. So that causes a financial hit to the scheme, which means the maintenance problem and operational problem become worse, and you get trapped in this vicious cycle. So the quality falls further, more people pull out. So to solve this, we said, okay, now we wanted to engage with the government, right? So it is not that, okay, just get an NGO, establish a private scheme, which may be needed at some time, but the large scale impact come when we can improve the government processes. So we started engaging with the rural water supply engineer to understand what are their constraints, what problem they face in carrying out their job. And of course, one of the things was that there are strict government norms for per capita cost. And when those norms are not met for whatever reason, then some corners are cut. So it's the importance of cost optimization dawned on us. And so we said, okay, if we can give you the best cost solution, that won't solve all the problem, but it would be useful. Also, each government, each year the district or a taluka has a fixed budget for water scheme. So if you minimize the cost, minimize the wastage, then more schemes can be designed, more people can be benefited. Furthermore, the technology gives us a foot in the door. So once you have a technology, you get a place on the table, and then even the social and the financial and the other issues, you have a say because you bring a different perspective based on all the experience of yourself and the group. And the other thing, sometimes the tools dictate the choices made also, right? So people follow a particular methodology, a framework that restricts what they can do. And therefore, if the tools were made for a different context, a Western context or some other context, then they may not be best suited because they drive the development in a certain way. So therefore, making our own system and tool was important. So in this interaction, we realized that, I mean, it's one thing to read about it in newspaper, but when we interact with people and government engineers, that there was a serious crisis in the drinking water sector, and even sometimes many places the basics of hydraulics is not known or whatever is misunderstood. The notions of optimization is not there. So they say as long as we meet the norm, we are enough. We don't have to reduce the cost further. That worry was not there. The tools were also not there. So all through, I will not be trying to blame the engineers. I am trying to describe the situation and the constraint in which they work. And of course, the productivity tools were just not being used. Furthermore, the audits are very important in the government. So they try to follow a strict protocol, and so that nobody can blame them. Why did you do this? Because our protocol says so. And these protocols are often rigid and frozen in time, sometimes 30, 40 years back. They were designed for a certain era, for a certain financial constraint, demographic environment, and those things have changed, but the protocols stay frozen. So in this context, and based on all the years of experience, I would say that this providing knowledge and tool is also a political act. It's a political response to certain kind of crisis that we talk about. So for example, one can blame everything on the caste considerations or political economy. But why does a village tank get built in one location, say next to the house of Sarpanch, and not in some other location? Uh, so one can just fight it at a political economy level. But one can also say, if one shows that that is not the right location, and here is another right location, if you are to meet the government norms for each of the person and including the so-called lower caste pada, which may be far away. So that becomes a response, another possible response to the situation. And we tell the people, look, what are the technical possibility? And then people have to take it upon themselves or demand from their elected representatives and the executive to deliver the services that government has offered. So in that sense, that has been our response, water group's response to some of these considerations. And therefore, we realize that our task does not end with the scheme design. Who receives our output is important to consider, because the utility of our work finally depends on that. Like many times I say, so much technology, so little development. So this has also been a journey in understanding the reasons and trying to find a solution to that. How does technology transfer happen? How should it happen? I mean, the manner of it. So anyway, coming back, our takeaway from studying this government design process was that there are strict norms, and there are several components of a water scheme I will talk about, but currently they were being optimized separately or designed/optimized separately or in isolation. And whenever they were using the software, so the rural departments, of course, could not afford the expensive software. So they were using mostly free archaic software with old technologies and with lots of limitations designed for, like I said, designed 20, 30 years back for an earlier era. And we're giving non-optimal performance and even erratic behavior. And further, it was not possible to improve those tools. So out of this came the realization that we need to build a free and optimal system. And we decided that it will be an open source system to optimize the overall water scheme cost. And now these pipes, the water pipes constitute a significant portion of the cost, water scheme cost. So in lot of scheme, those pipe diameter optimization is the main cost consideration. So we'll do that. But along with this, we will also optimize, try to optimize the storage tank, pump, and what. But this problem statement itself evolved over time. So I'm telling you what the problem statement is as of today. At the same time, it should be fast, free, and optimal, should handle large network of importance. But the usability is key focus. Right from the beginning, we knew that we will build a system to be deployed, to be used, not just to advance our research, not just as an academic project. So unless it has the usability features, the engineers are not going to use it. So the interface design, then using technology such as GIS. And furthermore, respecting the practitioner intuitions and constraints. So whatever constraints they face. So it's not, okay, given this problem statement, here is the best solution. When engineer says this cannot be done, that cannot be done, the system should be flexible enough to incorporate all those constraints and give the optimal solution with respect to those constraints. So the system has therefore a lot of configurable parameter selection. Okay, this place 10 can be made, this place it cannot be made, this place it must be made. Here the existing pipe, you have to add another pipe to an existing pipe. So a lot of such flexibility is built in system based on our interactions with the engineer. And of course, like I said, the attitude is to help government process, not just critique it. Right? So there are a lot of things are broken. Question is, how do we help fix them?
There's a question at this point, I think, that on
Sure.
chat.
Yes.
Could you share what a large problem means? That is the number of reservoirs, tanks, pipes, etc.
Okay, so maybe will come. These numbers will come in the talk later on as I talk about it. This will be answered. So remember, our focus has been on rural schemes. That's how we began. Now we are moving to urban schemes. So I will talk about that at the end. But I will give some numbers. So see, the components of a typical multi-village scheme are that, of course, there is a source from which water is pumped to a main tank, what's called a mass balance reservoir. From there, it can go to several tanks. These are the second level tanks that we see as we drive along the road, the elevated storage reservoirs. This is called primary network. And from there, it can go to nearby villages. So there is a secondary network, and then there is a tertiary network also, but this is sufficient for our purpose today. So the component that we are optimizing, that layout is taken as a given. So the main is, of course, the pipe diameters and the pumps. Where should the pumps be put? What should be their capacity? And then which village should be served from the which tank, and how big the tanks should. So where should we build these tanks? How big these tanks should be? What should be their height, capacity, etc. So if you look at the existing approaches, so this problem has been studied for over 50 years. And a lot of those approaches solve various components in isolation. We'll talk about why. And so they try to solve a specific optimal solution for some restricted problem. Like some people assume continuous diameter. See, these pipes naturally come in discrete sizes because only certain types of pipes can be stored for commercial regions. I guess they come in discrete sizes. You have to also manufacture them. So they assume continuous diameter, and then at the end of optimization, map it to the nearest available type. Or the other thing is that a large link can be broken down into two or more, multiple pipes of multiple diameters. But most of these problems assume one diameter per link, which is fine for most of the time. But there are a lot of scenarios where two links can be used and they reduce the cost. And then because these problems were being solved heuristically, a lot of genetic algorithm, meta heuristics, and other techniques were being applied. So when we thought about the problem, we said, look, these modern optimization solvers were pretty fast and they were getting even better with every passing year. This is early, like I'm talking about 7-8 years back. And we said, so we should focus, we decided to consciously adopt an approach of using this optimization solver and keeping our focus on model specification and refinement rather than on internals of optimization. So just the way like early on people used to worry hand translate high level programming code to assembly code, but the efficient compilers made that redundant and said you should focus on algorithmic complexity. Similarly, once the databases came, then we should focus on relational decomposition and indexing rather than the system level implementation. And more recently, model checking has again changed the nature of software verification, where you now again think about the abstraction. How do you specify a model for a program, software program at different levels versus a fine-grained testing or verification? So, I mean, this is a phenomenon that's happening in all areas of computer science, or I presume in all areas of any activity, this level of abstractions help. And this is the approach we decided to take. And then we decided, of course, but in the beginning, we said, let's first start small with the restricted cases. That was the common practice at that time. So just to restate and make sure you understand the problem. So it is a very simple network. There is one source and there are these three nodes. Each node has certain, these nodes are at different height. They have certain demand. And then these link lengths, there's some link length. The optimization problem. And there are three types of these pipes with a different diameter and they have different cost. Now, the pipe diameter decide the friction loss. See, what is the key problem? The problem is that the source supplies water from somewhere where there should be sufficient pressure available, then water reaches this node. So what we call residual pressure, right? So if the water at the ground should reach in rural area up to whatever is the norm, typically 7 feet or 7. So depending on the situation, it may be 7 up to 7 meter, but sometimes it's 5 meters, sometimes 10 meter or more. So that much residual pressure should be provided. This is what we call the head at the node. And the pipe choice determine how much pressure is lost due to friction. So that's what complicates the problem. And then of course there is a cost involved. Otherwise you could just use very large pipes and minimize the friction loss. So this is just the pipe selection problem. So which is what was being used most of the time. So this was our starting problem. Some exploration and discussion. So we formulated it and we said, let's start with the restricted case, which was a popular, that there's one pipe per link. And so there's an objective cost function for all the pipes. And then you select one of so there's an indicator variable, you select the pipe type, and then there's a cost for that multiplied by the length. There are pressure constraints that all the way from the root of the system source, all along the way, what is their pressure loss? This is the pressure loss formula, the Heisenberg equation. And then there are certain other constraints. So this is the very high level spec. There were, of course, a large number of constraints to model the system. Now, one thing is, so this was already known at the time that this is an NP hard problem. So that was known. So then we said, okay, so given that it is NP hard, what knowledge can we bring to the table? What restrictions can we put? I mean, this is already a restricted case, so it's, but there's a reason I'm saying that. So we again knew from literature that the one known result was that at most 2 pipe types are required if pipe cost is convex, which it is in all these water schemes. So therefore, we incorporated, you say, instead of 1 pipe per link, we said there can be going to be at most 2 pipe diameter. So let's include that. So the details are not important, but many of these terms get broken into two. You have two indicator variables, the pipe 1 and pipe 2, which pipes are chosen, and then you have to compute the pressure drop along them and all of that. But the problem is when we move from 1 pipe to 2 pipe, now it has become an NLP. See, you have this length variable, which is a continuous variable, and this X size, the indicator variable, which is a binary variable. So you have a product term here. So that was the problem. We said, fine, this problem can be solved. So this non-linear term can be linearized. And essentially, you introduce some dummy variable. So let's call this term a Zij. And then you said, okay, this can be decomposed using certain inequalities, which when the indicator variable is 0, their value becomes 0. When it is 1, it becomes the length of the total thing. So these details I will skip. But the problem is that this linearizes the problem, but now n into m decomposition are required. That is, for each link in the network, for each possible pipe diameter type, you have to do this. So your number of variables become a lot. Okay. So we were thinking what more to do. And of course, in the process, the lesson learned was that, as we will see, is that premature optimization is the root of all evil. So as we were thinking about the problem and looking at the formulation, so it turned out that we can actually get rid of these indicator variables altogether. And so we say, fine, even though we know the optimal solution will have only two pipe types, let's just allow all possible types. And the optimal solution, if the solver when the solver comes up with optimal solution, it will anyway have two types. So we don't have to restrict it. So the problem specification became simpler. And not just that, now it actually became an LP. So because it's an LP instead of an ILP, so the solution also came very fast. So that's what I meant by that. If we had started a general problem also, it could have been formulated in many different ways. And throughout the talk, I will talk about different ways of formulating a problem. All solutions give the same result, but they take different amount of time. So therefore, the model choice becomes important. How do you model the problem? So in this case, essentially what we are saying is a two-pipe approach has a lot many variables, and compared to the general approach, because of all these things we were trying, because we brought this knowledge of optimality that only two pipes types are going to be there. But you see, it resulted in a very large number of variables, and it was very slow. Okay. So this was the result of this model. Branch was the existing software of choice at the time. It could solve generally networks up to size 50, and then you can see the time taken. Whereas for large, so earlier it was asked what's a large network. So a network of size 100 was pretty much getting timed out on branch. That also depends on network topology, but on our test network, these were the result. And of course, size 1000 also it cannot be solved. Then these other models would time out. They could solve using size 100, but were timing out on 1000. But now we see literally in 2 seconds, we were solving a 1000 node network. Whereas in practice, probably 100 node network or so is as big as it gets. So, but we could solve even a 1000 node network in no time. So, okay, so that's the answer to the question, what we mean by large networks, generally hundreds of nodes. And things get more interesting as we bring in other components. So one of the thing now here is one of the interesting story here is that earlier we were using this LP solve library. Now this library, later on we realized that this was not the best possible library. So it was giving a poor performance on networks of realistic size, and hence we had to improve the formulation, and which we eventually did with the general approach. Now, the irony was, if we had started with a very fast solver, such as the current one, the CVC solver that we use now, then we might have stuck to that poorer approach and would have faced the problem later on when we extended the problem. So it's like many a time the fast machines can mask algorithmic inefficiencies. So it's important in any work that whenever we face performance problem, we immediately don't throw more resources at it, faster hardware, but first try to theoretically improve the model. So that was the lesson. So this was the JalTantra 1.0 version. This could be installed on for installment on a desktop. And so the rural water engineers in Thane district were started using it. We were interacting with them, like I mentioned, through the North Karjat experience. And we also started presenting the tool at various fora, one of which was a meeting called by CMO on water issues. And there was an engineer from Nagpur, Mr. Gavankar. He got very excited and interested. He visited IIT later, and then the MJP Nagpur office and Thane office started using it. And then the system improved with extensive feedback from these two offices. So this 1.0 version is still being used in some of the small offices for designing very small schemes. Now, around the time we had this NGO Kashtakari Sangat, so we were working on this. Like I said, all these things were going on TDSL project. We were looking at various schemes and also analyzing them from non-technical side. All these reports were on the web. So the Mokhada Taluka had a severe drinking water crisis, and these are all the tanker-fed villages in the Mokhada Taluka. You see all the red ones. And then, so there was a NGO called Kashtakari Sangathan. And they, on the web, they found that IIT Bombay is working on this problem as they were looking. So they approached us and said, all this water for Bombay comes from big reservoirs from Mokhada. But the irony is, a lot of tribal hamlets that are next to these reservoirs, they have drinking water crisis. So in fact, the crisis has been worsened because of the reservoir, but that's a separate topic. And furthermore, the government engineer said that this Mokhada Taluka is very hilly. So this hilly terrain makes designing piped water schemes unviable, that it doesn't meet the government per capita cost norm. And so they said, what can you do? So we said, okay, let's explore the alternative designs. And so generally, then we said, okay, so unlike the small schemes where there's only one tank, here, how many tanks should be there? Where should they be located? So this is just an example scenario where we say, look, there you can have just one tank to serve the whole taluka. I mean, this some small section of the taluka, the particular set of villages that we were studying at the time. And so ESR is this storage tank, remember, elevated storage reservoir. In scenario B, you can have 5 tanks, and that the scenario B has a higher cost by roughly 20%. But so what it means is that the where do you place the tank matters. So we decided to explore these alternatives, and essentially this was a tedious task because there are large number of, see, you could place tank in many places. They can be connected, different villages can be served by different tanks. So there was a location, height, capacity, set of the villages to be served, lot of issues. And these different choices lead to different costs. This was a huge, this is a problem of combinatorial explosion. So there are m nodes in the network, and then there are 2 to the power m configuration possible just of the tank locations. And then like height, capacity, and those are even different, further complications. And none of the existing water network design tools solve this placement optimization problem. So we decided to extend JalTantra by bringing this in our system support. So what matters? So here is an example. So again, in this case, like I said, there you can have just one ESR serving the whole network, or you can have one tank at each of the villages, each of the demand node. And typically the optimal choice will lie somewhere in between, like in this case, this 3 tanks suffices. So the aim is to find this optimal choice. Now this storage tank cost rises as the number of tanks rises. Intuitively, because the total capacity is fixed, So as you break it down into smaller parts, I mean, the cost goes up. That is the, because remember the cost function is again here is also a convex function. On the other hand, as the number of ESR rises, the piping cost falls. So I won't go in the technical details of it, but essentially the operational hours are different from what we call the primary network and secondary network. Because in a secondary network, I mean, primary network at the source, you have more operators taking good care. While the secondary network, if there are parts in a villages or tank, somebody has to go operate it. So they restrict it to a smaller number of hours. So the secondary network need larger pipe. So overall, the pipe cost falls as the number of ESR rises. And so we said, fine, we need to now model this tank placement problem. And so we discussed with the engineers as to what are the constraints, how do they think about this problem. And so then we made a model of this and what are the, so there are a lot of things about which tank can serve whom, what is the relation between it. So all these constraints were modeled. And then of course there is the issue of which tank will, I mean, which part of the network will be primary and which part of the network will be secondary. So this Fi is an indicator variable. So now once we did this, now you find that like we said, the optimal cost lies in between one DSR, just one ESR or a ESR at every node. So now they say in this network, if there are 20 possible locations for tanks, 13 of them were chosen to give the optimal cost. So the cost has gone down, but the time taken to solve the problem increased dramatically. So as we included, I mean, our new model has again become an ILP. Our general problem, just the pipe problem, was an LP, linear program. Now we have addition of binary variables again occurring in the product form. So this was an ILP, and performance was significantly impacted. Like earlier I said, it was literally in a second you could solve 1000 node network. Now 150 node network was taking 43 minutes, 200 node network we could not solve in over 4 hours. So you can imagine that earlier the water engineers would only explore some subset of combinations. They would not try all possible. I mean, obviously it's not possible. This is a huge combinatorial space. And so we said, okay, so we had to reduce time because this was clearly unacceptable. Because remember, this tool also comes as part of an iterative process, right? People try this, give some data, see what happens, and they have other considerations beside this formal model we have. So this time taken had to be small because it has to occur in an inner loop of some further optimization that I will talk about. So once again, we did that linearization of head loss equation like I described before, but now we went one step further. So this was not enough. And so as you study the problem and you say, okay, why is the linear relaxation of this not tight? So we did further transformations of the model, further refinement of the model. So instead of having this indicator variable about primary and the secondary network, we had this introduced the notion of primary length and secondary length. Essentially, the intuition was that here we are restricting for each link, whether it's, I mean, each pipe segment, whether it's in primary or secondary, we are restricting that, okay, it can be at most total length of the link. Now we said, look, this restriction can be put on the sum, not on the individual variable. So that's how the model was refined. But I will show examples of these intuitions may fail, that this may improve this part, but not other part of the model. So we also theoretically proved that this refinement is tight. I mean, this is a better refinement. This is indeed a refinement of this model. And so the wasted explosion doesn't happen. Similarly, there was this tank function. So tank again comes in the tank cost, the cost table for the tank up to a certain capacity. It will follow one form, then linear. So this is the cost function, form of the cost function based on practical consideration. So the similar techniques were applied to this and various refinements were done to linearize this also. So here is another example. So these were the type of constraints that we came by discussing with the engineers. Like they are saying these are the constraints, or we are taking notes or developing our own understanding and then translating them into mathematics. But when the performance was poor, so we were thinking about it and we say, okay, there are a lot of long distance dependency. We are talking about the relation between demand nodes in various parts of the network. Can we make this constraint local? So in various courses and theory of computation courses, you may have seen a discussion about what is a minimum description. Can you minimize the number of rules that will generate a given language or system? So similar ideas. So what I hope you see throughout the talk is that the ideas covered from different parts of computer science, that we have a very broad education, and that helps no matter which problem you work on. The elements and insights and the habits acquired from different sub-disciplines of computer science or of your education in general helps you. So in this case, it turned out all these three constraints can be replaced by a single constraint that a descendant is served is, and so anyway, that a node can serve a descendant only if it serves its child. So once stated, it seems simple, but that's not how the engineers initially thought about it, and neither did we. So only when we were forced to refine, we were thinking about all of it. And so a lot of such things were taking place. Essentially, we were looking at this model with hundreds of variables, equations, and say, is this necessary? Is this the best way to represent it? So, and there's some pursuit of what I call pursuit of simplicity and elegance. So one of the things we noted, there were some of the constraints were, see this road, a pipeline is laid along a road. So this goes ups and down. So there are artificial points. So when you want a linear segment. So when it goes up and down, you introduce this artificial dummy point. And those dummy points, typically the convention was that tanks is only placed at a demand node. So these were adding extra constraint. And then we discussed, is this really necessary? Why can't we put a demand tank at a dummy node? That means there's no village there. And of course, we asked the engineers and they were a bit intrigued or amused because they have never thought about it this way. So why should, this was natural to put it in a village. And they said, okay, sure, let's see if tries and improve. So it turned out that, again, it simplified the model further. And maybe for some network, depending on the topology, it will suggest those dummy points as the location. So several such improvements were made based on this philosophy, and that we continue today as we also design the urban loop network that I will talk briefly at the end. So we are constantly trying to apply this idea that what's the simplest possible model? What's a local model? How do we specify the constraints locally? Okay. So coming back, this model 4, as you can see, was just doing fine. A 200 node network, which was unsolvable in the earlier model, now just became very, very fast. So it's all a matter of seconds again. We are back to matter of seconds. So I would generally say anything larger than 50 node network is what we call a large network or 100 node network. Especially the earlier branch system could not, which was being used in large part of the country, could not solve a 100 node network. So what happened? So here was a feasible solution for Mokhara. So we organized a conference in the Khodala village in partnership with the NGOs. You can see our coordinators, Viraj Desai there and Professor Soni. And local people were invited and to take the initiative forward. And local MLA and MP were also present. And so we said, look, what we have shown to you that such a scheme for your taluka is possible. That just because it's a hilly terrain doesn't mean it has to cost a lot. Within the cost norms, it is possible. And Secretary Tribal Development Department also got involved, and then the task force was built. I was also the part of task force. And then anyway, various other things happened after that. The scheme changed. So we have given a feasibility report. Then they got convinced. See, till now, they were not even addressing the problem. Then based on their own considerations, they made several changes. But then recently the scheme could not be built. Before that, something else happened. The Samriddhi corridor in Sinnar Taluka came, and there was a plan to transfer Mokhada's water to Sinnar. So a lot of other things were happening. But at least the alternatives were now brought on the table because of our work. So this was the version that we publicized this years with optimization, and we again presented at various fora. And then we so as we were contacting various people, we contacted this in Rajasthan, the water comes under public health. So we gave a demonstration to them. And then they said, look, this gravity-based system is fine for your hilly areas of Maharashtra, but flatlands of Rajasthan, we have to use pumps all the time. So you have to, but your scheme, your JalTantra system was not dealing with the pump. So then we integrated the pump and valve in the design process. In fact, even Mokhada, like I said, this was just a subset of villages, because some villages which were at very height, we had to sort of artificially leave them out because we also didn't have the pump. So it was more an ad hoc process. But once we brought this in, all of them could be optimized simultaneously. So pipe, ESR, pump, valve, all of them could be optimized simultaneously instead of this manual iterative process. So why does pumping help? Of course, the obvious case is when your demand node is at a higher elevation than the source. So water has to be pumped up. So you say, okay, of course, how will water flow up? But even if the demand node is lower than the source, pumping can help because there is a friction loss, right? Because of friction, there is a pressure loss. So it is may possible. But the other thing, see, you don't have a choice of drawing a pipeline like this. You have to follow the road. But the other thing is it may reduce the cost. Even if this solution is feasible, it can reduce the cost. So optimal solution without tank may be like this, and the one with tank may be like this. Okay. But once you bring pumps in, then the operational cost also is matter, because the pump consume energy during operation. So that's why there is an appeal of, even if there is a slightly higher cost, there is some appeal of managing without pumps when you can. It's not just the operational cost, then maintaining the pump, then you need a pump operator. So all those considerations are there. But like I said, in Rajasthan, there's no option. So that's so once you have operational cost, then there is operational cost formula where you have to look at now the pumping cost and discount it. The future cost of it you have to discount to the present, and also your cost function changes, but it remains tractable. Okay. So that was really the final model we developed, and that is the one that is deployed for the rural branch networks. But we were still thinking, this is all those SI variable. I was showing a lot of constraints that looked very messy. And so we are saying, okay, is there an alternative model that might do better or might be cleaner? So the problem we are solving is really that this tank configuration has two components. One is partitioning the network into primary and secondary. Another is deciding how much capacity should each tank have, which demand node will be served by which tank. So it was this allocation of nodes to tank is what was being done by this binary variable. So essentially in a graph, we were focusing on the vertices. The alternative approach is to focus on the edges. And we said, look, instead of here, we are just saying that which pipe belongs to either a primary network or a secondary network, not the node. And so the model actually, just this aspect is dramatically simple. See, these 5 constraints get replaced by a single constraint, a single binary variable saying whether it's primary or secondary, and then some simple constraint. So we proved that this set is tight, that the linear relaxation is tight. However, this model did not perform as well, even though this is a tighter model, while the one on the left side is not tight. Because for this part, these constraints are improved, but the other part of the network, other part of our model got worse once we introduced this. So overall, this was good performance somewhere between model 3 and 4. 4 was our best performing model. So just some intuition that now because in an age-based model, the formula for the capacity of a tank got far more complicated, whereas earlier it was a very simple sum. So it's like, so that's why and then if you had to decompose it, there were a lot of equations, and so the overall model performance was not so good. Like it was good actually, better than our model 3. But the model we have implemented is the model 4. But as we deal with loop network or we do other extensions, we may come back to edge network, who knows? So because, depends on the various interactions and complications we further introduce in the model, right? As time passes by, user demand more and more feature. Okay, we can include this, that. So there is constant trade-off between keeping the model and the interface simple versus adding more and more features. We are following the philosophy of don't include all nice to have feature, but include everything that's necessary. And okay, so this was the JalTantra 2.0. Actually, this time we released both an online and an offline version because now the usage has increased many more. System had many more components. The installation, then you have to provide installation support, which version of, and a lot of things. So these are just some of the details. The web servlet, there was an optimization engine, and now we use the Google OR tool, so we could change the solver, and we were using the CVC solver. And we also did now a GIS integration. So now instead of just feeding the data, you can select the things on the map interface, and the tool will also automatically select a layout, a pipeline along the road. So this and then show you the elevation, the roads, and the nodes you are selecting from the elevation data from the Google. This is not always the most accurate, but at least this is good as a starting point when things are being explored and designed. For a large scheme, later on a real physical survey may be needed because the Google data is not accurate. Also, we are using the free version. So actually, it's not free also, free only up to a limited use. So which was the earlier the case. For last 2 years, we have been paying for it, even this limited refinement version. Okay, so this is sort of concludes my discussion of the rural branch network, which was how which was our main focus in the for most part of the decade. But then as people see the urban network, urban water supply departments generally has more resources, and the problems they handle are much bigger. So they use more, various other software. But the engineers started demanding or suggesting to us that, oh, can you also do loop network? Loop is the urban network or loop. By branch meaning acyclic network. In rural area, typically rural population is sparsely distributed. So you have one road and then the fields or the hills alongside. So there are no cycles. Whereas in the urban area, there are people everywhere. So all along the road, there are loops and cycles. So that's the urban network. Right? So urban network problem is significantly harder than the rural network. Why? Because in a acyclic network, the flow is fixed. So think about this. This is your source node. These are two demand nodes. Because the network is acyclic, there is only one path from the source to each demand node. And so that much water has to flow. But now if you connect, you make it a looped network. So now there is a cycle. So now both flow direction and flow value both becomes a variable. You don't know which one it is. Nature finds its way. Nature finds the balance because of this pressure loss equation. But a priori, you don't know. So for example, that earlier problem, now once we add this link, you can send more water along this path, and then part of it come along this and part of it come along this path. Or the other way, you can send more water here and then something goes here and something goes here. So that's why this unknown flow magnitude and makes this our constraints become non-linear, and the optimization problem becomes a non-convex problem, which is of course known to significantly hard, or there are no efficient solutions. But since there was a demand, people were saying that, oh, we would like to use this tool. Also, a lot of these small or large villages are now becoming the peri-urban areas are coming up, or the population is rising in rural areas. So the small municipality are coming up, a town with a population of 50,000 or so. So they have loop networks now. These small, large town already had. I'm saying even the rural areas now slowly start having loop network. So that's why there was a need that we work on this. So I will just very briefly describe this. What were the key ideas? So now there are cycles in these networks, and you have to worry about constraints along all of these paths. So one of the things was we have to reduce the number of cycles to be considered. And for this, we can use the cycle basis of the graph, like set of independent cycle from which all other cycles can be constructed. So restrict our attention to the cycle basis of the graph. Another thing we implemented is that separate the flow direction and the value. So you can have a single variable which indicates both based on its sign, or we say, look, really it's a composition of two problems. One is the orientation, in which direction should the water flow, and then how much water should flow. And so we solve this. So we said, okay, so first you solve it heuristically, get the orientation, then resolve it. And generally we found that it improves upon the result of original NLP. And finally, we modeled this flow, the single link with an unknown direction. We said it can be modeled as a parallel link, as if the water is flowing in two different directions. So I will talk briefly about this, and this was the approach that outperforms all previous approaches. Okay. So first, separating the flow direction from the value, right? So we say, okay, what are the different possible orientations in a graph, given a cyclic graph? Remember, now all possible combinations may not be feasible. Like if you randomly assign the flow direction, then you may have node which has only outgoing edges or only incoming edges. So that may not be a valid configuration in the context of water network. So therefore, so we have to do this search, this orientation space, and identify all meaningful orientation. So that's the algorithmic search. And then we solve the problem for each of this orientation, which is essentially a reduced system. So this is one idea. And then the other idea was that of the parallel link. Right? So each of this link we replace with two links. And then of course we know that one of the flow value has to be 0, but there are technical reasons that why this performs better than using a single link, the way these solvers work. So on one hand, at the beginning of the talk, I said we would like to abstract away and just focus on model refinement. But just like in databases, you have to know that how databases are implemented, knowledge of indices and other things to improve the performance. So in any model, the knowledge of the interiors of the solver helps. And so it turns out that essentially this is a visual representation. This is how we implement this in the model. And that turns out to be the best performing model. So this is sort of the summary without getting into technical details, that we have an input. Either we do a basic formulation or a parallel link formulation, then obtain locally optimal solution for each of them. So remember, this is an NLP problem, and we do not know. We do not get the optimal solution. Then extract orientation, or do an algorithmic search on the input graph and extract orientation, and then resolve them. And then we find that this PL and the resolved PL performs the best. Note that for loop network, we do not, neither do we nor anyone else has optimal solution. It's an NLP problem. It's a non-convex problem. But what we have is the best possible solution. And when I say best possible, meaning on test network, our approach performs as good or better than any other known solution. So there is no, that is the, so that's this is the best known solution. So on some network, a smaller test network that were benchmark network that were used, everybody gets the solution, which we don't know whether it's optimal or not, because, but everybody is getting that solution. That's probably the optimal. But on large network, our approach gives a better result than all other published results. So that's the sort of the summary of the technical, all the technical details of loop and branch network. And I will just briefly mention what are the different extensions possible. So of course, Professor Pradeep Kalbar and his students are working on introducing several new network elements, such as multi-outlet tanks, shaft, manifold, and then modeling them, modeling the pressure loss and other things along them. Then also we had joint student to model, they estimate the demand from GIS map, because these otherwise demand estimation requires surveys and other things, especially in dense urban areas. So at least some kind of cross-checking is possible. Then a standard problem is dividing a large network into multiple zones for maintenance and scheduling region. Inferring network topology from road network. So given a road network, given a dense road network, it's desired that automatically you infer the topology. And then scheduling is matters. See, what we have designed, assuming water will flow for a certain number of hours. In practice, it may not. So for operational reasons, that schedule may change. So IIT Madras, for example, the team, IIT Madras team is working on the scheduling of water delivery. Of course, there are a lot of such problems being worked on all over the world. I'm just telling you what's happening in the Indian context. And then there are big policy debates going on. So one is, okay, small village schemes, should they be based on groundwater or surface water? and the pendulum has been swinging between these two. Then should you make a large bulk water grid and then have other schemes use that grid as a source versus have a number of independent schemes? Similarly, actually now, so this last debate is resolved in Jal Jeevan Mission, but all these years we have been pushing that pipe should be taken to every household, whereas based on their experience and some orthodoxy, people wanted to only provide common taps and not pipe till the house, at least in our work areas. So that's the discussion. Thankfully, the work had some impact in real world. It's now being used as official design software in in Maharashtra, Rajasthan, West Bengal, Haryana. A lot of schemes have been designed using this. In fact, this is in continuous use since JalTantra 2.0 was released. And just in month of September, our server noted over 10,000 optimization calls. Of course, a lot of this may be just the testing and the students learning and people trying out, but still this use has been continuously just going up over time. So all kind of usage have been increasing, and now it's being used in National Jal Jeevan Mission also. As part of Unnat Maharashtra Abhiyan, many state engineering colleges were introduced to JalTantra, and they analyzed and improved the poorly performing schemes in their local area. So this compendium was brought out by the government of Maharashtra with UNICEF as part of the Unnat Maharashtra Abhiyan, and so we authored this compendium, and the Technology Development Solutions Cell of Sitara IIT Bombay, of whom I am one of the PI. So we have done design verification of hundreds of real life schemes, and so this continues to make the difference. And then as we interact with engineers, and they constantly keep telling us what they want, and so a lot of this thing, demand forecasting, automatic topology, inference, and of course I discuss extension to loop network. All of them we constantly are making this thing. And so the work has been recognized earlier by IIT Bombay, and more recently for the iForce Prize for OR in Development just few months back. So, and throughout this, we have been conducting training sessions for engineers. In fact, all through the COVID session, the online training sessions were being conducted, and now we have resumed physical training sessions. So anybody, any water engineering department, anywhere in the country wants us to conduct a training, we will. It would be great if you can bear our cost of travel and logistics. Otherwise, we will arrange some funds, but we want more and more people to use. So all of this was possible for two reasons. One is, of course, that we got a right team in place, that people, the faculty member, student from different departments with complementary skills and synergy came together. But other is that our explicit goal was that the system must be used, must be usable, it must be used. So constant interaction with the ground level practitioners, understanding their practices. See, if you go and tell them a better way, they are not going to do it. You have to tell them that whatever they are doing, what is their pain point, how do you help them? How will you make their life better? So that is our scope. And then slowly based on and then the rapport develops, and then also they listen to you, and then the two-way interaction happens. So a lot of these things, like I mentioned, happened based on the feedback or demands from government engineers. So all in all, I think it was a triumph of interdisciplinarity, where you see that different academic departments from IIT, Sitara, CUs, computer science, IOR came together. There is a consultancy cell that's explicitly engaging with outside world, technology development cell. There are various development research projects, TDS cell, and the academic research, MTP, RUTAG, and other things, which are doing case study. Then we interact with regional engineering colleges, and keeping stakeholder in mind, and keeping the last stakeholder in mind, and engaging with the government all along, because that's where finally the scale happens. Government has the scale despite whatever other problem it is. And it's government duty to help people, and it is our duty as public institution to help government carry out its duty. So that's all. Thank you. Be happy to take more questions.
Thank you so much, Om. Really amazing talk. There are already a couple of questions on the chat. So Sam asks, for loop networks, why can't we assume a direction and let the flow rate come out as negative?
We did that as a starting thing, right? So we have some internal representation. Like I said, that's just one of the model that we are trying, but the parallel link model performs better. Yes, that was the initial starting point indeed. So the internal reason is that when the flow value can be positive or negative, it can make a jump from the positive to negative. And our conjecture is too many of those jumps were happening. Once we break into two, you put a break at 0. So both sides don't, otherwise they are two variable, both have to change simultaneously and there are other constraints. So that doesn't happen. So that's why this breaking into parallel link is performing better. That's our guess. But yeah, in fact, that is what was our initial model has that only the baseline model has what you are suggesting.
Okay, and Adityan asks, can the digital elevation model generated from Cartosat-1 satellite data be used for elevation instead of paid Google data?
Yes, so okay, if the data is and you are welcome to help us with that. That's all I can say. There are a lot of ideas. We need people to try out different ideas, and only when we try out, we understand their limitations. So, but if anybody who can give us feedback, give us help how to do things better, of course, we will take suggestions, but all the more better if you join our team, collaborate with us, and actually give us at least a proof of concept or something. So yes, all help and feedbacks are welcome. So we have explored, we have thought about these things, obviously, and there are various practical constraints that we have been facing, but we are always willing to open those things again.
Okay, there's some more follow-up questions from Sam regarding solvers. Are you using Gurobi for ILP? Which solvers are you using for MINLP?
Currently, we are using the Baron and inside it's called IP opt. I mean, so the Baron and the Ample interface. But so the loop version is not deployed. So, right. And remember, this is a free system while these are commercial solvers. So anyway, so we are trying to figure out a way. The system has not been deployed, but we have contacted the Baron developers and saying that we are not charging for our system. What is the way out?
Okay.
But in fact, like I said, even the map API now our usage is so high that we are actually paying money from various sources. But the Google only gives you a limited number of map queries free per month. And our usage has thankfully become way higher, but we have to pay for it.
Yeah. So M. Patil asks, are you using EPA Net, an open source package that is used for water networks?
Yes. So EPA, when we say, see, this is a design software. EPA Net is a simulation software. In fact, a lot of people in the absence of those who are not using it, they make a heuristic design. Then they simulate it in the EPA Net to see whether it suits their purpose. So that's a standard design practice. EPA Net as a design in an iterative ad hoc loop was the practice. Whereas what we do is now we give you the optimal design. We in fact generate an EPA Net input file so that you can play with your assumptions. Scheduling is because at design time, you make a particular scheduling assumption. But once the network is generated, you can take the EPANET file generated from JalTantra and then simulate it with different scheduling assumptions and see whether any constraints are violated or not. And when we conduct training for government engineer, if we have more time, then we also train them on EPN. But
Okay.
any users of EPNet out there who have idea beyond the standard things about EPNet, once again, they are welcome.
Right. So Naveen asks, can we take each component in the water distribution network for optimization in a multi-objective context?
Yes, so we keep, of course you can. In fact, we have tried it. I mean, for our purpose. See, one thing is we are following the exact government methodology. So our deployed system does what the government protocols allow. But at the research stage, of course, we try many things. So for example, your goal may be that, okay, don't minimize capital cost. In fact, use, because government is, if that much money is there, of course, they will eat up from some other, but for this scheme, maximize capital cost up to the allowed limit if it helps you minimize operational cost. So that's something that we can trace. So you have a multi-objective function with different weightages that we have explored. That was included in our system. I mean, as a part of the research project. But deployed system strictly follow what the government methodology, because only then the government engineers will use. If it's a private scheme, then you can do whatever optimization, multi-objective optimization you want. And it's certainly possible to incorporate it. See, you are just changing the cost function. Of course, if that introduces various non-linearities, then you have to worry about it and refine your model.
So there is a question asking, when will you deploy the loop networks in JalTantra? And
Yes,
also,
we are.
if you can make some videos on JalTantra 2.0 available on YouTube.
So some videos are there in fact, we have made tutorial. We were pleasantly surprised that somebody, we don't even know who, but nobody from our group and nobody that anybody in our group know, made a tutorial on JalTantra and put it on YouTube. And we even found, some link from Indonesia. So we were very happy. So yes, but you are right that we should be doing much more than what. So like I said, the team is there, but the publicity and the usability aspect, making the training manuals and all. Right now we are physically conducting also, but we have to make videos. We have to make videos in Indian languages. Currently, we have our tutorials are only in English. So there are a lot of things, lot of work to be done.
And there was the question about when will you deploy loop networks?
I mean, we are also eager to, as soon as possible. That's all I can say. We also want to deploy.
Great.
But, also, this loop network take a lot more time. So what it means is even our server resources, we have to the independence, and then something may run for hours, you don't know. So, but our goal is to get it down to, we have gotten it down to second, but for some particular network configuration, it may take a lot of time. So we have to isolate the user. So a lot of constraints are there in loop network, which were not there from the server side, and then the licensing issue and other. We are working on all of that, and we will certainly be deploying it soon. That's all.
Great. Yes, this video will be uploaded on the FUSS site. And in fact, this semester we'll be making all the FUSS talks public after, of course, reaching out to the speakers and obtaining consent. Are there any other questions? So I had a broad question, Om, since you've deployed this in multiple states, were there any kind of geographical constraints which were different across different states? And then what were things which were common in terms of
Yes, so I told you.
demands?
So first, the system was developed for Maharashtra,
Yeah.
where we were focused on gravity-based schemes. So most of our rural scheme, because there's a hilly terrain, so most area you find some high enough place. And but when we discussed with engineers in Rajasthan, there is all flat land. So they said without pump we can. I mean, all our schemes use pump.
Right.
So that was the very first thing. That's how that later version came up. So then the other state like Haryana they have some proprietary software, the GIS software they use differently. So we had to do format conversion for them. So as such, some usually, but the pump thing came from Rajasthan, and other is different states. Some have different reporting format. So we have to generate report or the input format. So all of that we had to then facilitate for that. But no major difference was between this gravity versus non-gravity based schemes. This is an online system now. So in that sense, it's deployed on our server. But I mean, the 2.0 is also can be used offline. But I think now with faster net, everyone is preferring to use the online version. But it can be used in offline. The loop version will probably only be online. There won't be an offline version for licensing reason.
Right. Thanks. There are some more questions coming in now. Can we use the tool to identify stress and flaw points in the design of an existing network? And if not, can you suggest some approaches?
So it has been. Well, one is, of course, like we said, many colleges say they took the design document of a scheme and then they say, okay, given these constraints, let's redesign the scheme. And then what is the difference from the actually designed scheme? So many colleges did that and found those gaps. Other is that you can take some of the links and you say, okay, this link, because the pipes age. So we make some assumption about how much is the friction loss. With time, those pipes age and the friction increases. But sometimes you don't want to replace an existing pipe. So the tool then gives you flexibility that if I were to add a parallel pipe, what will happen? Will my overall system go down? Good. Do better, the cost go down if I can replace part of the system. But about the stress per se, like I said, there is practical issues of how much your pipe has aged, and there are many other considerations when you really want to measure stress. So JalTantra is just the design optimization software. Then you study this, bring that in, and at time the EPANET is very helpful because that's a simulation software in that stress analysis. But like I said, a lot of colleges have used JalTantra and EPANET and have given feedback. And there was a special workshops we organized for all these colleges, and that the TechWhip World Bank TechWhip program and UMA facilitated program. And we helped a lot of them to carry out and analyze the failing local schemes and suggest and make suggestions for improvement. So EPANET based simulation to be short answer, but you have to visit the scheme, figure out which components are failing, make some guesses, and what is the friction loss. At times you have to do measurements also. So I didn't go that part because my focus was on the software side of it. But you saw there are teams with people from very different background. Like the very first TDSL student, Abhishek and others, is a civil engineering student, and he's doing PhD in CUs now. And so we have done a lot of pressure measurements and other things. And Abhishek and Anuj have a lot of ideas about how to improve those networks also. So get in touch with us later on. It need not be part of the JalTantra now, but there are others in our group who can help, who may be able to help.
Okay, I'll just combine two questions. Have you considered valve design? Have you followed the empirical rule for valve locations? And can the system be used for piped irrigation networks?
So valves are modeled in the system, but again, based on our interaction, they are, I mean, there's no cost consideration. The valve itself is for taking care of the excessive pressure. So there are, we have finally any system is an abstraction, and there are some practical things that for various reasons engineers want to do it ad hoc fashion, a valve being one of them. So the system has valve incorporated. It makes suggestions about where the valve should be placed because there is a the pressure constraint is being broken along certain pipe. There is a maximum pressure that the water should exert on the pipe or the pipe will burst. So it makes suggestions, but it does not make it mandatory. And that's how the engineers wanted. So they said, give us suggestion, we will take the call. So that was about the wall. The second question you asked about
Pipe
agricultural
irrigation.
water.
Yes.
Yeah, so pipe networks, in fact, it has been used for pipe irrigation by some people. So as long as it's a closed pipe, then you can use it. Open channel fluid dynamics is different. So it cannot be used for open channel irrigation, but closed pipe network it's the same thing, right? Our focus of our work has been on drinking water, but there is a source, water is transmitted through a pipe network, and then whatever use it is put. It's fine. So it has been used for agriculture. In fact, currently there is a Professor Priya Jadhav of Sitara, there is a MTech student who is using it for agriculture pipe network.
Okay, and there's one last question. In JJM, we have to retrofit existing rural water supply schemes. How can it be done with existing pipelines and parallel pipelines?
It does. The system gives you an option to say, see, for everything, the system allows you to say whether something can be done here, whether something cannot be done, and whether it must be done. For tank logo, similarly for the pipes, you can say either, okay, ignore this pipe, put a new pipe, or you say this is an existing pipe, put a parallel pipe here. So then the system will, if it makes sense, system will try to put a parallel pipe. So this retrofitting need again came from the ground, and people have been using this. So the retrofitting feature is there. Please use it and give us feedback as to if that suffices your purpose, or whether if somebody has a need of a different kind of retrofitting, then we'll see if we can incorporate it. But this has sufficed so.
Okay, I think those are all the questions. So if there are no more questions, let's thank the speaker again. Thanks so much, Om, for an amazing talk. I truly think it is a triumph of interdisciplinarity, and look forward to hearing more about the system in the coming years.
Thank you, Preeti,
Thank you,
for
everyone.
organizing the talk and sending me
Thank you.
reminders. I must talk. And thank you.
Thank you. Thank you, everyone, for attending.
Thanks everyone for joining. And as I said, please not just now, join us later, give us feedback, use the system, and find all its fault and help us improve it. Thank you. Thank you all.
Thank you.